All right, friends, welcome back. In this video, I'd like to go ahead and take a look at section 5.3 of your textbook, and that's going to talk all about the laws of logarithms, aka all the rules of logarithms or the properties of logarithms, whatever you want to say. And I want to go ahead and start off by taking a look at a way that you guys can be calculating your logarithms using any calculator, okay? So it turns out that specifically in the TI-84, it does have the functionality to be able to calculate a log with any base. To do that, you just want to go ahead and press alpha, window, and then you want the fifth item in that list, so just press the number 5 key, and it'll pull it up for you. And you can see here that you have prompts for both the base of the logarithm and for the input. It gives you the ability to go ahead and take a look at an example like the one we're about to look at, which is the log base 4 of 30. And if you press enter, it'll actually perform that calculation for you really easily. The unfortunate thing is that all scientific calculators don't come equipped with that functionality. So for example, the standard calculator that comes with Windows 10 can do some logarithms, but not all, right? You could do the common log, which remember from the last video is your base 10 log. It could actually also do the natural log, which is your base E, Euler's number. But unfortunately, it can't really do anything much besides that. So what we're going to need is a way for you guys to be able to calculate logs using any base you like, and that's what we use this change of base formula for. So just kind of honing in on this really quickly, you can go ahead and take a look at a log with the base of 10. Again, we call that your common log. If you wanted to go ahead and perform the log with any base of any input, then you could just go ahead and simply follow this formula here. You notice that we're doing the common log of the input over the common log of the base, and that'll actually give you the exact same result. If you don't want to work in base 10, but on a scientific calculator, if you have base E or the natural log, you could set it up in the exact same way. The log with any base of any input is just going to be the natural log of the input over the natural log of the base, okay? So to go ahead and just demonstrate that here to you, we got this decimal expansion in the calculator by doing the log base 4 of 30. Let's go ahead and do that with the common log. So in the TI-84, that's the button that's to the left of your number 7 button. That's your common log. So we're going to do the common log of the input, 30, divided by the common log of the base of 4. And you can see that it gives us the exact same decimal expansion. Not only can we do that with the common log, we could also do that with the natural log. So just to demonstrate that, the natural log of the input, 30, divided by the natural log of the base, which is 4, and press enter, and it gives us the exact same decimal expansion, okay? In the Windows calculator, you'd have to type it in a little bit of a different way here. We would want to go ahead and first type in the input of 30, and then the common log of that, and then divide that by the base of 4, the common log of that, and then press equals, and then it gives us the exact same decimal expansion there, okay? So sometimes, depending on what scientific calculator you're working with, you're going to have to type it in a specific way, but we should be getting the same result no matter what we are typing it in as. And that actually is going to be the solution to example 1, the first part, okay? So you can see here that it's going to ask us to change the log base 4 of 30 to a base of E. Again, base E logarithm, we call that the natural logarithm and say ln. We already did that calculation. That turns out to be 2.45, okay? Doing something similar here, we could take a log base 2 of 0.04 and convert that to a base 10, your common log, which I've already done here for you. I'm not going to take you to the calculator and demonstrate that because it would be the exact same calculation. But the point is, regardless of what calculator you're using, maybe it's the one that's on your phone, maybe it's a scientific calculator you've been using since elementary school, what have you, you can always go ahead and evaluate the log with any base of any input. The next slide here talks about your laws of logarithms, and so if you work with logarithms enough, you might start to notice that you have some certain patterns or certain things you can say that are always true about logs. And so specifically, I'd like to go ahead and hone in on 3 specific properties that we're going to be using extensively throughout the rest of the chapter. And so let's go ahead and talk about each one right now. So a couple of words about what you're seeing here. You're going to see a lowercase letter a representing the base of these logarithms, and that just is a for any base, meaning that these properties will work no matter what base of logarithm you're going to be discussing. A couple of things about what we want that base to be. It says up here in the preamble that we want to let a be a positive number, not a negative number. And we also don't want a to be 1, and that's the same reason as, you know, in the last video whenever we had your exponentials and we said your base of your exponential probably shouldn't be 1 because that's not a very interesting case, right? Also in these properties, you're going to see capital variables of a, b, and c. We're going to just let those be real numbers, and we're going to need a and b to be positive in order for these properties to work out for us. So what you're going to notice here in this first property is it's going to say log base a of, and then it's going to say capital A times capital B. Okay, and so what we're going to characterize this property as is anytime you have the input of your log being represented as the product of two things, right? So something times something else. So I'm going to phrase that as the log of a product is always equal to what? Well, we can always split this up, split up the two inputs that we were multiplying, A and B, and change the operation to an addition between two separate logs. This is actually a property that is always going to work no matter what the base of your logarithm is, just assuming that capitals A and B represent positive real numbers. So that's how I like to characterize that. The log of a product is the sum of the logs, and it works similarly if you have a quotient, right? So if your input is represented by the division of two positive numbers. So the log of a quotient, we can always go ahead and split that up into separate logs as long as we change that operation from division to subtraction, okay? And I want you to understand here that this is actually something that's pretty profound, right? We haven't really taken a look at a lot of ideas or functions in the past that can do this sort of thing. It can take a product and turn it into the sum of two things, right? So these are actually pretty profound. But then the last log property that we're going to go ahead and take a look at here is what you're going to call your power property, and this is actually kind of a weird one that's specific to logs, but it says if you take the log of an exponential, say a to the power of some number c, what this property allows you to do is take that exponent and write it in front of the log so that you're saying that number c times the log of a with et cetera, right? So again, that's not really a property that a lot of other types of functions have. These are the ones that are specific to logarithms, and these are the ones that we're going to be demonstrating as we go throughout examples, okay? A couple of non-properties, these are ones that classically students have always kind of had some confusion about or made some mistakes on. It turns out that the log of a sum is not the sum of the logs in that first case. The division of two logs is not going to be equal to the single log of a quotient. And if you raise the output of your log machine to the power of 3, that's not the same thing as writing that exponent out of front. What we would need is for the input to be raised to the power of c in order for us to go ahead and write that out in front. Okay, so a couple of non-properties there. But I just wanted to take a look at a couple of examples here where it says here in the directions, use the laws of logarithms to expand the expression, okay? And so really quickly, what we mean by expand is this. What we're going to say here is that we're going to take an expression that involves a single log of something, and we're going to go ahead and write that as an equivalent expression, but involving multiple logs, okay? So maybe like a log of something plus or minus the log of something else. So basically, in other words, we're going to take an expression with a single log and rewrite it so that it involves multiple logs. And so just to demonstrate how that's done here, maybe take a look at the first example, a log base 2 of an expression like 6 times x. That is, of course, a product, and we have that property that says that I can go ahead and split this up. Say the log base 2 of 6 plus the log base 2 of x, okay? Again, if it's a product on the inside for the input, it's going to be the sum of the outputs of your logs there. So remember, that's always a property of logs that we can point out. The next couple of examples I already have worked out just for the sake of time in the video here, but one of the things that I always want you guys to be doing is if you see any sort of roots in your expression, I always want you to convert those to the exponential forms of those roots, right? So we have those properties that just basically tell us how we can deal with the log of an exponential, but we don't really have clear properties that tell us how to deal with the log of a root. And so this is one of those applications where we're going to need to be able to convert from the root language to the exponential language here. So square root of y, I'm going to rewrite that as y to the power of 1/2. And you notice here that I am doing the log of a product, so I'm going to go ahead and rewrite that as the sum of the logs. Okay, so log base 5 of x cubed plus log base 5 of y to the 1/2 power. And you can see there in green, I'm going to be applying my power property next to take those exponents on my inputs and write them in front of my logarithms. And so I'm going to have this final result right here. So 3 times the log base 5 of x plus 1/2 times the log base 5 of y. So again, when we expand, we took originally an expression that only involved a single log, and we rewrote it in our final answer to involve more than one log. Okay, so that's what expansion means. Here in this third one, we have the natural log of a to the 4th divided by b times the cube root of c. Remembering always to change any roots you see into its exponential form, so that will be c to the power of 1/3. And the first thing we're going to work with here is going to be that quotient, that fraction bar, right? Because that remember represents division, and so our input here is a quotient. We're going to rewrite that as the difference of two logs, and so the natural log of a to the 4th minus the natural log of b times c to the 1/3 power. And what we're going to work with next next is going to be this part right here. Okay, so this second log, remember that we can go ahead and see here that the input is a product, so I can go ahead and split that up into the natural log of b plus the natural log of c to the power of 1/3. But the thing about that is that we are, of course, subtracting away this sum. So when we do that, we're just going to have to make sure to distribute this minus sign to both terms of that sum, and so this sum in the middle is basically going to change to a difference down here whenever we do that, okay? And then finally here we have some exponents on our inputs. We're going to go ahead and use our power property to put those in front of the logarithms, and this would be our final result for part C, 4 times the natural log of A minus the natural log of B minus 1/3 the natural log of C. Okay, and so you know that you're going to be finished when you look at the inputs of your logs and you recognize here that you don't have anything else to do. Your inputs are not written as products or quotients, and your inputs are not also not represented as exponentials. Okay, so you've done all that work, and you're able to get your final result in that way. Again, a couple of more worked out examples here. What we're doing here is we're now condensing. Okay, so you're going to have to pay attention to the language of the directions. This is working backwards from expansion, which means, again, we're going to take an expression involving multiple logs from the start, and we're going to condense it down to an expression involving only a single log at the very end. Okay, and so here in this first example, you have 5 times the common log of x plus 3/4 times the common log of x plus 1. We're going to go ahead and use our power property first to write those as exponents on our inputs. Okay, and so we're going to have the common log of x to the 5th plus the common log of x plus 1 to the power of 3/4. And now because I'm doing the sum of two logs, I can go ahead and condense that down into a single log by remembering to find the product of the inputs of these two logs individually here. So that would be the common log, the single common log of x to the 5th times that quantity x plus 1 to the power of 3/4. Okay, as another example here, we might see this one here. We might see 3 times the natural log of a minus 4 times the natural log of b squared plus 1 plus 2 times the natural log of the product c times d. First thing I'll do there is I'll use my power property to go ahead and rewrite those numbers in front of the logs as exponents first on my inputs. And then you'll notice there that I highlighted that difference or that subtraction in yellow because we always want to take care of whatever operation comes first as you read from left to right. And so I'm going to go ahead and rewrite this difference of these logs as a single log of a quotient, okay, using my quotient property there. So that is going to be the single log ln of a to the 3rd over b squared plus 1 all raised to the 4th power. And now because I have a sum of two logs, I'm going to go ahead and apply my product property. If it's the sum of the logs, and that's going to be the single log of the multiplication of the inputs. And you notice there that I'm going to be taking an a to the 3rd all divided by b squared plus 1 all raised to the 4th. I'm going to be multiplying that times this fraction that I highlighted over here. So that's the cd squared all over 1. When you multiply your fractions, you're just going to multiply the two numerators and then multiply your two denominators there, and then you're going to get this final result, the natural log of a cubed times cd squared all over b squared plus 1 all raised to the 4th power. Okay. In the next example like this one here, we always want to work with what's inside of the square brackets or what's inside of your grouping symbols first before we do anything else. So you can see inside of those square brackets there, I'm going to have the sum of two logs with a base of 7. I can go ahead and condense that down by multiplying those two existing inputs there. So just real quick, if you were to multiply your x minus 5 times x plus 5, you might recognize that as the difference of two squares formula, which is why you see me having written there x squared minus 5 squared, or in other words, minus 25. Okay. What we're going to do next is, now that we've condensed what's inside the square brackets into a single log, we're going to take that 2 out in front, and we're going to rewrite that as an exponent on the input of that log. So you can see that that's what I did in the next step. And then finally, I am performing the difference of the logs here, so I'm going to go ahead and write that as a single log of a quotient. Okay, so final answer there is log base 7 of w divided by x squared minus 25 all squared. Okay, so when you're condensing, that is going to be a quick demonstration of that type of idea there. Next example, example 4, is a common type of question here. Again, this is just more expansion, and we are going to see that this is a multiple choice question. Okay, so we have choices A, B, C, and D here. Let's go ahead and work with what we've got and demonstrate some steps here to get our final result here. So we're going to notice, first of all, that we have a root in the problem. So this is going to be the 5th root of y. We always want to go ahead and rewrite those as exponentials. So y to the power of 1/5 to start us off there. And then we are dealing with a log base 8 of a product. Okay, so we're going to be multiplying x to the 3rd times y to the 1/5. And so I can break that apart into the log base 8 of x to the 3rd plus the log base 8 of y to the 1/5 power. And then after that, the next step of this work would be to go ahead and do our power property, where we're taking these exponents of 3 and 1/5, and we're going to go ahead and write them in front of the logs there. Okay, and so our final answer is going to be 3 times the log base 8 of x plus 1/5 times the log base 8 of y. Okay, and that's going to be our final result there. And it looks like, if we look at our multiple choices, that is going to correspond to a choice C there, it looks like. Okay, so we're going to go ahead and circle C there in that work. Okay, so again, if I give you a multiple choice question, just be very careful as you look at each choice, because they all look very similar. But again, just kind of taking a look at what we ended up with there, that is going to be our result. All right, so example 5 here, we just want to go ahead and do the exact same thing, except we are going to be condensing in this problem. And so we notice here first that we have a couple of numbers in front of logs that we can go ahead and rewrite as exponents on the input. So take that 2 and put it on an exponent of x, and then take that 4 and put it as the exponent of x minus 6. And so continuing here, we're going to have the log base 10, or the common log. I'm not going to write those base 10s ones because those would be assumed, but this would be the common log of x squared minus the common log of the quantity x minus 6 to the power of 4. Okay, and now because I'm doing the difference of the logs, I can go ahead and condense that into a single log by saying the single log of x squared divided by x minus 6 to the power of 4, and that is going to be my final result there. And you can see here that that is going to correspond to a choice of A from the choices given. Okay, so so that's pretty easy, right? And then finally, what I want to do here is some examples where we are finding the exact value of these logs, but without using a calculator. Okay, so what that means is that we're going to be applying the properties of logs to specifically work with these algebraically, instead of reaching for a calculator and getting a decimal expansion for these. Okay, and so if we're working with these, in part A, we see the log base 3 of the 5th root of 27. Remember, we're always going to write our roots in terms of their exponent. So we're going to rewrite this as the log with a base of 3 of 27 to the power of 1/5. And again, another reason why we might do that is so that we can use our power property and write that power out in front. So we can continue here by saying 1/5 times the log with a base of 3 of 27. And the interesting thing about this is that log base 3 of 27 is actually something that we can work out. If we go ahead and rewrite your 27 as something with a base of 3, then that's something that we can use one of our log inverse properties from the last video to go ahead and simplify here. So 27 can be rewritten as 3 to the power of 3, and if we're doing the log base 3 of 3 to the power of 3, then that's simply just going to be 3, and that's going to leave us with the final result of 3/5. Next one down, the common log of 25 plus the common log of 4. That is the sum of two logs, so I can go ahead and condense that down to the common log of 25 times 4, because remember, if it's a sum on the outside, then it's going to be a product on the inside, and that's going to be the common log of 100. And remember, since the base of this log is 10, if I go ahead and take this input and rewrite it so that it is an exponential with a base of 10, then I'm going to be in shape, right? And so 100 is something I could go ahead and rewrite as 10 squared. And so because the log base 10 and the base of the exponential is 10, I can go ahead and say here that my final result is simply just going to be 2, no calculator required. And then in this last example, same thing. We're just doing the difference of two logs with a base of 3. I can condense that into a single log with a base of 3 as long as I go ahead and do 36 divided by 4. And of course, that's going to give me 9. So this is going to be the log with a base of 3 of 9. And same reasoning as before. If I could take this 9 and rewrite that as an exponential with a base of 3, then that's going to be something that cancels nicely for us. And so 9 is something you can also rewrite as 3 squared. And so the log with a base of 3 and the exponential base of 3, those cancel each other out, just leaving us with the final answer there of 2. Okay, so using these log properties, we can do problems like this in a very much easier way than having to reach for a calculator and having to type those in a tedious way. So I hope this video has been helpful to you. If you guys have any questions, then please do not hesitate to let me know. But that's all I have for this one. Thank you very much for your attention, and I'll speak to you in the next one.